Hello there. Let's talk about graphs in the context of data structures and computer science. I just want to talk to you about some of the basics of graphs, some ways that we could implement them in the future, and some terminology. Okay, so for starters, we have a little blank graph sheet here. If you saw my previous video, you'll know already that this is a valid graph. It's just totally empty. There's nothing on it. But let me draw some data in this graph. So graphs are collections of nodes and edges, or vertices and edges, or vertex and edges. The nodes themselves, they are custom classes sometimes, other times not. But you can imagine that they hold some sort of custom data. So I know I did this in my last video, but I just want to emphasize that this graph class, if we're talking about C++, it should be a template class, meaning we can specify a custom data type that the nodes will hold, and also a custom data type that the edges will have as their weight. Typically when you see examples of this in the wild, it's just going to be integers, but you could do other data types like floats and strings, exotic custom classes. Depending on your use case, it may or may not be useful to do that. But so we'll have a data type for our nodes, and I'll call it like N type for like our node type. And then we'll do another one called E type for edge type. I don't know if that's the best way to write those, but I'm just going to do it anyway. Imagine that your graph, like we said before, is a collection of nodes and edges. So I'm going to put a node class here. You could imagine this as a vertex class. And I'm going to say that this node holds an n-type data, and we'll just call it data, or node value, or whatever you want. And then the same thing for the edges. We'll say we have an edge class. I think in my last video, instead of doing a node class, I did a vertex class. It's kind of all the same. We'll say we have an E-type, and we'll call it weight, or value, or data if you want, but I think weight is a little bit closer to what we're going to actually be doing with it. And what do I mean by N-type and E-type? Like, what are those data types there? That just means these are placeholder tokens. So when the user actually uses your graph by making an instance of your graph class, like they create an actual graph off of your blueprint class here, they might decide that they want integers inside of their nodes. So that's what I'm going to do right here, integers. They might decide that they want floats inside of your nodes, inside of their nodes, or some other data type. And so that means like at runtime, or I think actually at compile time for C++, this N type would actually change to int if they chose to use integers on the inside. Same thing would happen for the edge. Whatever they choose for the E type token is just going to end up being used at compile time to replace that E type. So I don't know, here's an example. I got a fly in my room. It's bothering me. Imagine the user says, I want a graph, and I'll call it G. And so they just have to kind of specify the two data types. Maybe they want the graph to have integer values in the nodes, and maybe, floating point, double precision floating point values on the edges in terms of weights. You could do something like that. But anyway, so we have nodes and we have edges, and this graph right here is valid. It's just one node kind of floating around by itself. This graph is also still valid, even though we have two nodes that are floating unconnected and also with the same value. I'm just going to change the value to be different. Maybe I'll get rid of this extra thing here. So this is a valid graph still. We could have like a whole bunch of nodes all over the place, and they don't really have to be connected. This is still a valid graph. I'm going to change this to like a 3, maybe change this to like an 11. Change that to a 6. What else can I change? How about like a 13? How about like a 17? Are there any duplicates? I don't think I see any. All right. So this is a valid graph. The next thing that we could add to our graph is edges. So edges are, little mini data structures that connect nodes. In this particular graph, I'm choosing to not have direction on my edges, which means this is a special type of graph. There are 4 that we talked about in the previous video. This is unweighted and also undirected, meaning there's no weight assigned to the edges. which means that template weight value, or the weight data type that we just talked about before, it's kind of useless for this particular graph because I'm saying it's unweighted. And all the edges, if we wanted to travel through the graph along the edges, we could just sort of go in any direction we felt like. So this is unweighted and undirected. Let's see, what else can I show you real fast? Okay, so let's talk about, well, really fast, let's talk about the uses that you can have for a graph. I think I talked about this in the last video. But, you know, what can we use graphs for? Some people think they're databases. They're not really databases. You could technically do that, but it would be pretty slow. There are much better data structures for databases. Really, what graphs are mostly used for is to represent relationships between different things. I think I said this in the last video. Imagine if every single node that you see here is a city, and the edges represent flight paths. So we could fly between city 7 and 11. Oh, that's funny. I'm hungry for a candy bar now. We can fly between city 7 and 11 and back in the other direction if we want to, but we can't actually fly from city 7 to 6 because there's no edge there. So we could represent computer networks, we could represent road maps, airports, dependency graphs, game maps. You could say like every node is somewhere your character could stand, and an edge represents where your character could move, or it represents a connection to another node so that you know your character could move there. There's all sorts of different things that you could represent with the graph, but it's not necessarily a fast database. It's more of like a relationship. Not to be confused with relational database, which is supposed to be lightning fast. Like if I wanted to search for the number 17 in this graph, it's not going to be log time like a proper database should be. It's not going to be constant time like a hash table-based database should be either, or like a NoSQL or whatever. So we have undirected and unweighted. We talked about like different uses. Let's talk a little bit about terminology. Okay, for starters, notice how there's no hierarchy in this graph. In other videos, we're going to talk about binary search trees, and we have to have like a hierarchy. There's no parent, there's no child in these graphs. There's no, like grandchildren, ancestors, descendants, because there's not really like a hierarchy. It's just things are connected to each other or they're not. But we can have something called neighbors. For example, if you can reach a node in one hop, then you might be able to call that a neighbor. So 6 and 17, those are neighbors. Maybe I'll just type neighbors right here. Oops, neighbors. Because we can reach them in one hop. Later on, or especially if I don't remember to mention this, if we add direction to our graph, then something is only considered a neighbor if you can reach it while respecting the direction of the graph. So we have like neighbors as 6 and 17. So that means 6 and 11 are also neighbors. 6 and 12, not neighbors, because they can't reach each other in one hop. Let's see. Adjacency is basically the same thing. I can't remember. I think we use adjacency more often in directed graphs, but we could say that 6 and 17 are adjacent to each other, which is in this context sort of a synonym for neighbors. Okay, something else that I want to talk about in terms of edges. Edges are considered to be incident upon nodes or vertices. So like, if I have an arrow that just kind of points to these two things, I could say, edge is incident upon 3 and 12. It just means, what are you touching? It's incident upon 3 and 12. Okay, what else should we talk about? We should talk about connected versus, no, that's another video. Okay, I'm going to do another video for connected versus not connected graphs. Maybe I should mention that there are 3 ways that we can represent a graph, and then maybe I'll upgrade to a directed graph in a second. If you want to know about the 4 different types of graphs, see my previous video. But for now, I'm going to say there are 3 ways we could represent these graphs. The first way, and I'm talking about how can you represent these graphs inside of the machine? Like how can your computer store and process this graph and maybe run algorithms on it? So the first way that we could represent, at least that I'm going to talk about, is an edge list. Edge lists are super simple. I'm going to do a dedicated video just for edge lists in the future. They're not very fast, but they're very easy to implement. So honestly, if you're just starting with this stuff, I would recommend just implementing an edge list first. The next thing that you can do to represent a graph in the machine is make an adjacency list. Adjacency lists are just a little bit more complicated, but they're typically faster than edge lists. Not always, not in all cases, and in terms of time complexity, you might not feel like you notice much of a difference. But empirically, adjacency lists just kind of give you the option of skipping a lot of examinations. When you don't need to examine something, you can kind of skip it. We'll talk more about that in the future, but we have an edge list and an adjacency list of representation. And then we have an adjacency matrix. I wish I had spell check on this, otherwise this is going to be humiliating. An adjacency matrix is sometimes a lightning fast representation of a graph. At first you might think, wow, that's amazing. I'm always going to use that. But all of these representations have strengths and weaknesses. None of them are better than the others in every single circumstance. So, computer science and data structures, it's all about weighing the pros and cons and picking the right representation or algorithm or whatever that's best for you and the code and the data that you're actually going to run. So 3 different ways that we can represent a graph in the future. And let's see, we spent 12 minutes already on this. We talked about the basic ways to use them, sort of. We talked about neighbors and adjacency. Oh, I got to upgrade to a directed graph real fast, just to kind of show you the difference here. Okay, so I'm going to duplicate this. And I'm just going to start adding direction to all my edges. In my previous video, we talked about this. If you add direction to even one edge, then you have to add direction to all the other edges. Otherwise, you will have an invalid graph. So notice how I added direction to one edge. I now have an invalid graph. So I'm just going to do this. Change every single edge so that every single edge has a direction. The basic thing, we kind of talked about this in my previous video, is that when traveling through the graph, you're supposed to only be able to travel in the direction of an edge, which means if you look at this thing right now, you're supposed to be able to go from 11 to 7, but you're not supposed to be able to go from 7 to 11 because that violates the direction of the edge. When we add direction, we're sort of like reducing, the flexibility of the graph. So you can imagine that the previous version that was undirected, it was sort of like every single edge here was really 2 edges pointing in opposite directions, if that makes sense. So if you wanted to make sure that you could go back and forth between node 7 and 11, well, just add another edge going in the opposite direction. You can also do things called parallel edges, which is just to say, I'm going to add multiple edges that go in the same direction from the same start node to the same end node. But I'm not going to do that here. That makes it more complicated for some representations. But we can just sort of add a whole bunch of edges. I'm just going to say one going back and forth there, and so forth. Remember in my previous video, we talked about weighted edges, which means we could add a cost to traveling along an edge. So you could say something like, I don't know, going from 7 to 12. Let's add another edge here. If there was a cost on all these weights, maybe I should just add that for fun. We could maybe calculate which path would be better. So let's say we got 1s over here, and we got 5s over here, and maybe like a 2 here, and then 6s here, and I'm going to do like an 8. By the way, these 6s don't have to be the same. You could just be 2 different numbers. So I'm going to do like a 3 here, and let me just see, have I added a weight to every single edge? So I know I did this in the previous video, but I want to do it again real fast. If we chose to take a path from 7 to 12, and we said 7 to 11, and then 11 to 12, that's a very specific path, which is, it's going to cost us 5 to go along that first, edge, and then the second edge is going to cost us 6, and we're only traveling along 2 edges, so the total cost of that path is 11. On the other hand, let me actually make this look pink. On the other hand, if we're taking a different path, we might come up with a different cost depending on the graph. So let's say we start at 7. Maybe we want to go down to 3, and then from 3 we'll go to 12. Well, that might be a different cost. So I'm going to say the cost of this particular path is traveling. It's going to cost us 1 to go down that first edge, and then a 2 to go down that second edge, which means the total cost of getting to 12 is only 3 if we take that orange path versus 11 if we take that pink path. I hope you're starting to visualize how graphs might be useful to visualize costs. If this is a network map, we just figured out that one route through the network might be faster or less costly than the other. Or if this is like an airport map, maybe you do want to take, that layover that goes down south instead of that layover that goes east in terms of, I don't know, frequent flyer miles that it costs you, or money it costs you, or jet fuel that it costs the airport, or whatever. So, I think that's all I wanted to talk about in this video. I'm going to make one more video today. Well, it'll be released, I don't know when, but like in my present moment. I'm going to make another video right after this where we just talk about connected graphs versus not connected graphs. Thank you so much for watching this video. I hope you learned a little bit of stuff and had a little bit of fun. See you in the future. Okay. In the future. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. Sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? Just send me a comment. Whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness, which is coming for us all.